September 2015 from the Free State. Question 8. The graph below is obtained from an experiment to calculate the internal resistance of a battery. So we have a graph of current versus the potential difference. 8.1.1. Calculate V internal if the current in the circuit is equal to 0.2. The current is 0.2. So we want to know what the potential difference is when the current is 0.2. So the potential difference should be equals to 2. So V external should be equals to 2.0 volts when I is equals to 0.2. Okay. The value of the EMF is measured when no current flows in the external circuit. Wherever we have the current as 0, we are going to look for the corresponding potential difference. At this point, at 3.0, the current is 0 and then the voltage is 3. So the EMF should be 3.0 volts. EMF should be equals to V external plus V internal. The EMF is 3.0, V external is 2.0. So this means that V internal is equals to 1.0 volts. 8.1.2. Calculate the internal resistance of the battery. EMF should be equals to the current multiplied by the R external plus the internal resistance. So we are going to manipulate this equation so that it becomes a representation of the graph. So EMF should be equals to V external plus IR. IR should be equals to the EMF minus V external. This implies that I should be equals to 1 all over R multiplied by V external plus 1 over R multiplied by the EMF. So I is in the y-axis, and then negative 1 over R will represent the gradient. V external is found on the x-axis, so we can see V external there. So it must be on the x-axis, so this will represent the x, and then this whole thing will represent the y-intercept. So we have an equation of a straight line. The internal resistance, we can see that it must be the gradient. The gradient should be equals to negative 1 over R, which is equals to the change in current all over the change in potential difference. When the current is 0.6, the voltage is 0. And when the voltage is 3.0, the current is 0. So this is 0.2. So we need to find the inverse of this because this is 1 over R. So I'm getting, that's the value of the internal resistance. This is option 1. You can even use, so for the y-intercept, you know that for the y-intercept, 1 over R multiplied by the EMF should be equals to the y-intercept. The y-intercept is 0.6 at that point. So all of this should be equals to 0.6. The EMF is 3. So 0.6 divided by 3, I'm getting 1/5. Therefore, the internal resistance should be 5.0 ohms. 8.2. A circuit is connected as shown below. When switch S1 is closed, V external is equals to, should be equals to 22.5 volts. The internal resistance of the battery is 0.8 ohms. And then the value of the EMF is 24, right there. Let's analyze the circuit. This is the positive side, that's the negative. So the total current will flow in this direction. Still, we'll have the total current, and then at that junction, the current is going to be divided in I2. There's no current that will come in this direction because they only said that switch S1 was closed, meaning that S2 is still open. The current is going to combine again, and then the current through I3 should be the total current, I total. 8.2.1. Define Ohm's law in words. So the current that's flowing through a conductor is directly proportional to the potential difference across its ends, provided that the temperature remains constant. 8.2.2. Calculate the power dissipated by the 16 ohm resistor. Okay. In this case, we have the EMF, we have V external, and the internal resistance. So it's possible for us to calculate the total current. EMF is equals to V external plus I multiplied by the internal resistance. EMF is 24, V external is 22.5. The total current, that's what we're trying to get, multiplied by 0.8. I'm getting 1.875 amperes. So this is the total current. When we look at the circuit, if we combine R and the 16 ohm resistor, the parallel combination will be in series with a 3 ohm resistor. Our circuit will look like this. We will have something like this, R parallel. So in this part we have combined the 16 and then the R resistor, so they become one resistor. This is the 3 ohm resistor. For resistors connected in series, they should have the same current, but the potential difference is divided. So we can find the voltage through the parallel combination, and we can also find the voltage through this one. When we add these two voltages, they should give us V external. So it's possible for us to calculate the voltage through the 3 ohm resistor because we have the total current. The current is 1.875. The resistance is 3. I'm getting 5.625 volts. We said V external must be equals to V parallel plus V through the 3 ohm. V external is 22.5. Then V parallel plus 5.625. V parallel should be equals to 16.875 volts. Let's take the parallel combination now. We have R there, and here we have the 16 ohm. We have current I1 and current I2. For resistors that are connected in parallel, the current is divided, however the potential difference is the same. So it means that the voltage through the 16 ohm resistor is 16.875. Now we can find the power. We use this formula. (16.875) squared divided by 16. I'm getting 7.80 watts. 8.2.3. Calculate the resistance of R. We will try two different options. That way, if we get the same answer, then our working would be correct. Okay, we have option 1 and we have option 2. In the first option, we will use EMF must be equals to the current external resistance plus the internal resistance. The EMF is 24. The total current is 1.875. Yes. R external, we do not know. This is 0.8. Getting 12 ohms. Then for the parallel combination, we take the value of the first resistor, which is 16, we multiply it with the second one. Then we find the sum. And then we said that the R parallel will be in series with the 3 ohm resistor. So we can say R external should be equals to R parallel plus the 3 ohm resistor. This is 12, 16R, 16 plus R plus 3. This becomes 9 multiplied by 16 plus R getting 144. I'm getting 20.57 ohms. This is the first option. Let's try a different one. We know that for a parallel combination, the current is divided. So let's calculate I2 because we already have the potential difference. I2 should be equals to V over R. The voltage is 16.875 and then the resistance is 16. I'm getting 1.05 amperes. And then I1 should be equals to the I total, The I total should be equals to I1 plus I2. I total is 1.875. I1 is 1.05. Therefore, I2 should be equals to 0.83. And then now we can calculate the resistance. The voltage is 16.875, and then the current is 0.83. 16.875 divided by 0.83, 20.33 ohms. So they're pretty much the same. So our working must be correct. 8.2.4. Switch S2 is now closed. We are closing off switch S2. Remember, the total current is coming in this direction. How will the voltmeter reading V1 be influenced? Write down only increase, decrease, or stay the same. Give an explanation to your answer. Well, current always flows in the direction where there is less resistance. So the current, it will not go in this direction because we do have resistance there. It will also not go in this direction because we have resistance in the 16 ohm resistor. So the total current will flow in this direction and then go back, then all the way around. So there'll be no current that's through there. So we are removing the parallel combination altogether. This means that R external decreases. When the resistance decreases, the current increases. From this equation, you know that I times the R external, I multiplied by the internal resistance. The EMF and the internal resistance do not change. So when the current increases, it means that V internal should go up and then V external should go down. Therefore, V1 should what? Decreases. It should decrease.